Welcome to the course Design of Reinforced Concrete Structures. In today's lecture, we are going to solve a problem on limit state of collapse torsion. That is, we are going to solve a problem on torsion reinforcement. So, the question given here is, design the reinforcement required for a beam of size 300 mm by 600 mm. So here what? Here a beam is given and the size of the beam is 300 mm by 600 mm. And that particular beam is subjected to a factored bending moment of 150 kilonewton meter. So it is what? It is subjected to a bending moment mu. Here the value of mu is given, which is 150 kilonewton meter. And the factored shear force of 100 kilonewtons. So here what? The shear force, the factored shear force is also given, that is Vu is given, which is 100 kilonewtons. And factored torsional moment, that is what he is asking to design for the torsional reinforcement. So the torsional moment is also given, which is 50 kilonewton meter. And the grade of concrete is M20 and the grade of steel is Fe415. So what here is asking? He is asking to design the reinforcement required. So what is the reinforcement required for that particular beam? If we have a bending moment acting on it, the factored shear force as well as the torsional moment. So first we will start with writing down the given data. So what are all given in the question? The breadth of the beam is given. How much is the breadth of the beam given? It is 300 mm. And the depth of the beam, that is the overall depth of the beam, capital D is given, which is how much? 600 mm. And the factored bending moment, that is mu is given here. How much it is? 150 kilonewton meter. And the factored shear force. So what is the factored shear force? Vu. So Vu is given. How much it is given? Vu is given as 100 kilonewtons. And the torsional moment, that is Tu. Tu is given. How much is the torsional moment? It is 50 kilonewton meter. And the grade of the concrete is given. So what is the grade of the concrete given here? It is FCK is M20, that is 20 Newton per mm square. And the grade of steel is given. What is the grade of steel? It is Fe415. In the sense, Fi is given, which is 415 Newton per mm square. And what is asking to determine here is asking to find out the reinforcement required for this particular beam when all these moments and the forces as well as the torsional moment is acting. So first what? We have known the breadth D and we have known the overall depth D, but we don't know the effective depth D. So first let us calculate the effective depth D. So what is effective depth? Effective depth, how we can calculate the effective depth? D. It is denoted by D. So effective depth D will be equal to overall depth minus the effective cover. So what? I already know the overall depth D, which is what? 600 mm, but effective cover is not known. So what we will do here, we are going to assume a suitable effective cover. So here what I am doing, going to assume a suitable effective cover, and I am assuming an effective cover of 30 mm. So how much is the effective cover I am assuming here? I am assuming an effective cover of 30 mm. So what will be my effective depth D here? 600 minus 30, which will give you 570 mm. So what is the effective depth D here? Effective depth D is equal to 570 mm. So now I have calculated the effective depth D. So what is the next step? That is the first step. What we have to do when we have to design for the torsion? We have to calculate the equivalent shear. So let us calculate the equivalent shear. So the first step, what you have to do is we have to calculate the equivalent shear. So the step 1 is to calculate the equivalent shear. So how the equivalent shear is denoted by? It is denoted by VE. And what is the formula for calculating the equivalent shear? VE is equal to VU plus 1.6 TU by V, which is given in IS 456-2000. So from this can we calculate VE? So VU is already given, TU is already known, and the breadth of the beam is already known. So substitute all the values here so that we will get the value of VE, which is nothing but the equivalent shear. That is the equivalent shear force VE is equal to VU. How much is VU? It is given, it is 100 plus 1.6 into TU. What is TU? TU here is nothing but the torsional moment. So what is the torsional moment here? The torsional moment is 50. As these are in kilonewton meter, I am converting B into meters. So what is B here? 300 mm, which is 0.3 meters. So if you solve this, you will get a value of VE as 366.667 kilonewtons. So what is the value of equivalent shear here? The value of equivalent shear VE is equal to 366.667 kilonewtons. So now what we have known the equivalent shear force VE. So what is the next step? What we have to do? We have to calculate the equivalent shear stress. So this is the equivalent shear force, that is VE. Okay, we have calculated the equivalent shear force. Now we are going to calculate the equivalent shear stress. So the next step is what? We have to calculate the equivalent shear stress. So now the second step, what we have to do is we have to calculate the equivalent shear stress. So how it is denoted? It is denoted by tau VE. So the equivalent shear stress tau VE can be calculated by using the formula VE by BD. It is what? VE by BD. So we have already previously calculated the value of VE. So what is the value of VE? VE is 366.667 kilonewtons. So substitute the values here. Okay. So tau VE is equal to 366.667 into 10 cube newtons divided by B. How much is B here? B is 300 mm into D. What is D here? D is nothing but the effective depth, which is 570 mm into 570. So from this you are going to get the value of tau VE. So calculate this and you will get the value of tau VE as 2.144 Newton per mm square. So if you solve this, you will get a value of tau VE as 2.144 Newton per mm square. So now we have calculated the equivalent shear stress tau VE. So next what we have to calculate? We have to calculate the tau C, that is shear strength of the concrete, as well as we have to calculate the tau C max, that is the maximum shear strength of the concrete. We have to calculate the tau C max, that is the maximum shear stress of concrete. So first we will calculate the tau C max. Now let us calculate tau C max. So tau C max, what is tau C max? Tau C max is nothing but the maximum shear stress of concrete. So how can you calculate tau C max? Tau C max can be calculated from the table 20 of IS 456-2000 for different grades of concrete. So what is the grade of concrete here? The grade of concrete here is M20. So as the grade of concrete is M20, we have to check for the corresponding tau C max value in table 20 of IS 456. So from that you can get a value of 2.8 Newton per mm square. From where? From the table 20 of IS 456-2000. So what is the value of tau C max? It is 2.8 Newton per mm square. Now what we have got the value of tau B. So let me write down the value of tau B here. So what is tau B? Tau BE, that is the equivalent shear stress value we have got. It is 2.144 Newton per mm square. And what we have seen in the previous lecture, we have seen that tau BE, that is the equivalent shear stress, it should be less than the tau C max. If it is more, that is, if tau BE is greater than tau C max, then what you have to do? You have to redesign the section. The design and all should be redesigned. So it is not acceptable. So here from this particular, from this particular thing, what you can observe, that is from these particular values, what you can observe? You have the tau BE value is 2.144 and tau C max value is 2.8 Newton per mm square. So from this you can observe that tau BE is less than tau C max. So as tau BE is less than tau C max, hence it is okay. Hence it is what? Okay. So you can go for the further design. So if tau BE is greater than tau C max, the whole section it has to be redesigned. That is the breadth and depth, everything should be redesigned. So as tau BE is less than tau C max here, so hence it is okay and we can go for the further design. Now what? We have seen the equivalent shear stress and we have seen the tau C max, that is the maximum shear stress of concrete. Now we will calculate, in the next step we will calculate the tau C. Tau C is nothing but the shear strength of concrete. So let us calculate the tau C. So tau C is what? The shear strength of concrete. So from where you will calculate this tau C? Tau C can be calculated from the table 19 of IS 456-2000. Okay. So tau C can be calculated from table 19 of IS 456-2000. So in table 19 of IS 456, what you will have? For different grades of concrete and for different percentages of steel reinforcement, you are going to have the tau C values. So first what we have to know? We have to know the percentage of the steel reinforcement. That is the percentage. That is, we have to know the percentage of area of steel reinforcement. So here in this particular problem, if you see, the reinforcement details are not mentioned here. So the reinforcement details is what we have to find out here. So for calculating the tau C, I am assuming some area of steel, that is some percentage of area of tensile reinforcement. So here what I am assuming is, I am providing or I am assuming the area of steel reinforcement as 0.5%. Okay, that is the percentage area of steel reinforcement. I am considering it as 0.5%. So now for the 0.5%, the corresponding grade of concrete for M20 from table 19 of IS 456-2000, I am taking the tau C value. So for this percentage area of steel of 0.5% and for the grade of concrete M20, the tau C value will be 0.48 Newton per mm square. So this is my assumption. So you can assume this area, percentage area of steel, either you can assume it as 0.75 or you can assume it as 1. So anything which is present in the table 19 of IS 456-2000. So here I have provided the percentage area of steel reinforcement as 0.5%. So for that corresponding percentage of steel reinforcement and for the grade of concrete M20, the tau C value I have taken here it as 0.48 Newton per mm square from this particular table. So now what? I have got all the values. I have known the equivalent shear stress, that is tau E, and I have got the value of tau C, that is the shear strength of the concrete. Now what we have to do? We have to compare the tau E value and the tau C value. So based on these two values, we will know whether we have to provide the minimum or the nominal reinforcement, or we have to design for the torsional reinforcement. So first let us compare the tau E value and the tau C value. Now what we have to compare the tau E and tau C values. So if you observe here, what you can observe here, that tau E is greater than tau C. So if tau E is greater than tau C, for this condition what? We have to provide the torsional reinforcement. So what? If tau E is greater than tau C, then the torsional reinforcement, in the form of longitudinal reinforcement and transverse reinforcement is to be provided. So what? If tau E is greater than tau C, what? You have to provide the torsional reinforcement. And how the torsional reinforcement is to be provided? That torsional reinforcement is to be provided in the form of longitudinal reinforcement and also the transverse reinforcement. So now what? Now we have to provide the torsional reinforcement. So first what? We will provide the longitudinal reinforcement. So the next step is to calculate the longitudinal reinforcement. Now what? We have to provide the longitudinal reinforcement. So the step 3 is to provide the longitudinal reinforcement. So to provide the longitudinal reinforcement, first what we have to do? We have to calculate the equivalent bending moment. So first what we will do is we will calculate the equivalent bending moment. So the equivalent bending moment ME has to be calculated. So what is the formula for calculating ME, which is given in IS 456-2000? It is ME is equal to MU plus MT. That is the movement, the bending moment, considering only the dead loads and the live loads, and this is the bending moment considering the torsion. So that is the equivalent bending moment ME will be equal to MU plus MT. So first what? MU is already given here. So what is MU? It is 150 kilonewton meter. But MT is not given here. So first what we have to do? We have to calculate the torsional bending moment MT. So what is the formula for calculating the torsional bending moment MT, which is given in IS 456-2000? MT is equal to TU into 1 plus D by B divided by 1.7. So this is the formula for calculating the torsional bending moment, that is TU into 1 plus D by B divided by 1.7. So we already know the value of TU. TU is nothing but the factored moment. So the factored torsional moment is TU, and D is already known. D is nothing but the overall depth of the beam, and B is the breadth of the beam. So substitute all the values here so that we will get the value of MT. So TU, how much is TU? It is 50 kilonewton meter. So that is 50 into 10 to the power of 6 into 1 plus D. What is D here? D is 600 mm divided by B is how much? It is 300 mm divided by 1.7. So from this you will get a value of MU. So what will be the value of MU? So if you solve this, you will get a value of MT as 88.23 kilonewton meter. So what is the value of MT you got here? It is 88.23 kilonewton meter. So this is your torsional bending moment. So now you can calculate the equivalent bending moment. That is equivalent bending moment ME is equal to MU plus MT. So MU you already know, which is 150 kilonewton meter, and MT you have calculated now, which is 88.23 kilonewton meter. So substitute in this so that you will get the value of MU. So now let us substitute the values of MU and MT. So MU is equal to MU plus MT. So how much is MU? MU is 150 kilonewton meter and MT is 88.23 kilonewton meter. So from this you will get a value of ME as 238.2 kilonewton meter. So this is going to be our equivalent bending moment ME, which is 238.2 kilonewton meter. Now what? We have two conditions here, whether we have to provide the minimum or the nominal reinforcement, or we have to provide the main reinforcement. So now what we have to do? We have to compare the MU and MT. What we have to do? We have to compare the MU and MT. So if you compare the MU and MT, what you can observe that here we can observe that MT, that is the torsional bending moment, is less than MU. That is what here the torsional bending moment is less than the MU. So what is the value of MU? It is 150 kilonewton meter and MT is 88.23 kilonewton meter. So here what, MT is less than mu. So if MT is less than mu, so what, from this condition there is no need of reinforcement to be provided in the compression zone. So what, no need of providing compression reinforcement. That is, simply you can say that this is a singly reinforced beam. Like you can design by using the same formulas and the equations what you have used for the singly reinforced beam. So what we have to do now, we have to design for the provision of reinforcement only in the tensile zone. So it is considered as a singly reinforced beam. So if MT, if it is greater than mu, then what, there is an additional moment here, then you have to design for the additional moment also. So in that case you are going to have the compression reinforcement also. You have to design for the provision of the compression reinforcement also. So now as the condition MT is less than mu, there is no need of designing for the compression reinforcement. So we can design this particular longitudinal reinforcement considering the singly reinforced condition, singly reinforced beam, and the reinforcement we will design only for the provision in the tensile zone. Now what? The next step is to calculate the area of the steel reinforcement. Now what? Now we have to design the longitudinal reinforcement to resist the equivalent bending moment MB. So now what? Let us find out, the next step is to find out the area of the steel reinforcement required for resisting the equivalent bending moment. So the step 4 is to calculate the area of steel required to resist the equivalent bending moment. Why? Because MT is less than mu, because we have got the condition that MT is less than mu. So the longitudinal reinforcement, it is to be provided to resist this particular equivalent bending moment, which is ME. So now what? Let us calculate the area of steel. So I will calculate by using the equations as we have used in the limit state of collapse flexion. So what? ME is equal to 0.87 Fy into AST into D minus 0.42 XU. So in place of XU, you have to substitute what? XU is nothing but 0.87 Fy into AST divided by 0.36 into FCK into B. So in place of XU, what you have to do here? You have to substitute this, that is 0.87 Fy into AST by 0.36 FCK into B. And you have to calculate the area of steel, which is, let us substitute the particular XU here. So if I substitute XU here, what it will be? It is 0.42 into 0.87 Fy into AST divided by 0.36 FCK into B. So all the values are known here except the area of steel. So area of steel is what we have to calculate here. So substitute all the values. ME, we have ME. How much is ME? It is 238.2 kilonewton meter. So I am converting it into 10 to the power of 6. So ME is 238.2 into 10 to the power of 6 is equal to 0.87 into Fy is how much? It is 415 because the grade of steel is 415 into AST into D. D is how much? It is 570 minus 0.42 into 0.87 into Fy. How much is Fy? It is 415 into AST divided by 0.36 into FCK. How much is FCK? It is 20 into B. B is how much? It is 300. So if you substitute all the values here, you will get a value of AST. So AST, if you solve this particular equation, you will get a value of AST as 1394 mm square. So you will get a value of AST as how much? It is 1394 mm square. So this is the area of the steel which is required for resisting this equivalent bending moment. So this is what? This is the area of steel which is required. So this is the required area of steel is how much? It is 1394 mm square. Now what? We have calculated the area of steel required for resisting the equivalent bending moment ME. So what is the value we got here? That is AST required is 1394 mm square. Now what we have to do? We have to check for the minimum and the maximum tensile steel reinforcement. So first we will check for the minimum area of steel reinforcement. So how? What is the formula for this? It is AST by BD is equal to 0.85 by F1. So yeah, we already know the value of B which is 300. We already know the value of D which is 570 is equal to 0.85 by 415. So from this we will get a value of AST, that is the minimum area of steel reinforcement, which is 350.2 mm square. In the similar way, we have to calculate the maximum area of steel reinforcement which is to be provided. So what will be the formula for calculating the maximum area of steel reinforcement to be provided? It is 0.4 B into D. So what is B here? B is 300 and D is 600. So if you calculate this, you will get a value of 7200 mm square. So always the AST required, it should be in between these two. So here what? The AST minimum is 350. So we have provided more than that, and the maximum is 7200, and what we have got is more than the maximum area of the steel reinforcement. Now what? This area is the area what it is required for resisting that particular bending moment. Now I am going to assume a suitable diameter of the bar, and I am going to calculate the area of the steel to be provided. So what I am doing is I am assuming diameter of bar as 20 mm. So the diameter of the bar, how much I am assuming here? It is 20 mm. Now I am going to calculate the number of bars required for this particular AST of 20 mm dia. So I will calculate n into pi d square by 4. D here is how much? 20. Divided by 4 is equal to 1394. So from this you will get a value of number of bars as 4.40, which approximately we can take 5 number of bars. So here we have got 4.43, but we cannot provide 4.43 bars. So that is the reason why I have approximated it to 5 number of bars. So here what? The number of bars we are providing more. So what? The area of steel is also going to change. So here I am going to calculate the area of steel which is provided. So I will calculate n into pi d square by 4. So what will be n here? 5 into pi into d. How much is d? 20 whole square divided by 4. So if you will calculate this, you will get a value of 1570 mm square. So what? The AST, that is the area of steel, what I have as a longitudinal reinforcement I have provided. The AST is how much? 1570. So what is the minimum? The minimum area of steel is 350.2 mm square. So minimum is this. So I have provided more than that, and the maximum is 7200 mm square, and I have provided less than that. So the AST provided should be always in between the minimum area of steel and the maximum area of steel reinforcement which has to be provided. Now what? How many number of bars I am providing? I am providing 5 number of bars, and a dia of each bar being 20 mm in the tensile zone as a longitudinal reinforcement. So as it is a singly reinforced beam, so a nominal dia of bar should be also, or nominal bars has to be provided in the top, that is the compression zone also. So here what I am doing is I am providing in additional to this, I am providing 12 mm diameter bars each on both the corners in the compression zone also. So here what? In addition, I am providing 12 mm dia bars on both corners in compression zone. So provide 12 mm diameter bars on both the corners in the compression zone also. So what, when we provide the stirrups, we cannot provide the stirrups only if there is a bottom reinforcement. So we have to provide minimum dia of bars so that the stirrups can be holded properly. So for that reason I am providing minimum bars, 2 bars on both the corners, okay, and the dia of the bar being 12 mm. Now what? We have found out the longitudinal reinforcement. So and we have provided the longitudinal reinforcement. So what is the longitudinal reinforcement what we have provided in the beam? So if this is the beam section, the width of the beam 300 mm, the overall depth of the beam is 600 mm. So now what we have provided the reinforcement, longitudinal reinforcement in the tension zone. How many number of bars we have got? We got 5 number of bars, and the dia of each bar being 20 mm. So provide 5 number of bars. So here I am providing 5 bars. So 5 bars, each of dia is 20 mm diameter, and we are providing 2 bars of 12 mm diameter on the top. So here we are providing 2 bars each on one corner. And what is the dia of these bars? It is 12, 2 bars, 12 mm So what we have designed for the longitudinal reinforcement. Now what? As per the clause 25.5.1.7 and 25.5.1.3 in IS 456-2000, if the depth of the beam is more than 450 mm, you have to provide the side reinforcement. What if the depth of the beam is more than 450 mm? Then what we have to provide the side face reinforcement. So here the depth of the beam is more than 450 mm. Is it or not? So for this reason, what in this particular beam section we have to provide the side face reinforcement. So what we have to provide the side face reinforcement. So now let us design the side face reinforcement. So as per this clause, what is given is the side face reinforcement, that is the area of the side face reinforcement should not be less than 0.1% of the area of the web. So what? The area of side face reinforcement, it should not be less than 0.1% of the web area. So for that, what I am doing is I am finding out the area of the side face reinforcement, taking it as 0.1% of area. 0.1% of area of the web or area of the beam section. So now let us find out the side face reinforcement. It is 0.1 into the area. What is the area? It is 300 into 600 divided by 100. So 0.1%. So 0.1 into 300 into 600 divided by 100. So if you solve this, you will get the area as 180 mm square. So how much is the area of the side face reinforcement you have to provide? It is 180 mm square. So here let me assume that the diameter of the side face reinforcement be 12 mm. So I am assuming that the diameter of the side face reinforcement is 12 mm. So from this what I will do? I will calculate the number of bars. So I will calculate the number of bars n into pi d square by 4. Here d is how much? D is 12. Whole square divided by 4 is equal to 180 mm square. So from this what you will get? You will get the number of bars n. So if you solve this, you will get the value of n as 1.59. So the number of bars what you have to provide is how much? For this particular side face reinforcement area is 1.59. But we cannot provide 1.59 bars. So for that reason I am approximating it to 2 number of bars. So how many bars I am providing? I am providing 2 bars on each side of diameter 12 mm. So in the middle I am going to provide 2 bars. So these are the 2 bars of 12 mm dia which I am providing as a side face reinforcement. That is, this is the additional reinforcement what I am providing due to the depth is more than 450 mm. As the depth is more than 450 mm, this is the additional reinforcement what I have to provide as per the clauses 25.5.1.7 and 25.5.1.3 in Annex 456 2000. So I have provided the additional side face reinforcement and two reinforcement bars of 12 mm diameter I have provided as side face reinforcement. Now what? The longitudinal reinforcements we have designed. Okay. Now what? We have to provide the transverse reinforcement which we have already discussed. What? The torsional reinforcement, it should be provided in the form of longitudinal reinforcement and transverse reinforcement. So the longitudinal reinforcement is what we have provided. Now we will move on and design for the transverse reinforcement. So the next step is to calculate the transverse reinforcement. Now what? We have to provide the transverse reinforcement. So how transverse reinforcement is provided? Transverse reinforcement is provided in the form of stirrups. So let us find out the transverse reinforcement. So ASV. So what? The transverse reinforcement is what? It is provided in the form of vertical stirrups. So here I am going to find out the area of the vertical stirrups. So to find out the area of the vertical stirrups, I am assuming that a two-legged stirrup of 10 mm diameter. So I am going to provide what? I am going to provide what? A two-legged stirrup of diameter. How much it is? 10 mm diameter is provided. So I am providing what? A two-legged stirrup of 10 mm diameter. So I am going to calculate the ASV. So ASV is what? 2 into 5 d square, that is 10 square divided by 4. So if you solve this, you will get a value of 157.07 mm square. So this is nothing but the area of the vertical stirrups what I am going to provide. That is, I am going to provide a two-legged stirrup and the area is 157.07 mm square and the dia of the stirrup is 10 mm. Now what? Let us calculate the spacing required for this ASV. So what is the equation for calculating the spacing? That is ASV is equal to TU into SV divided by B1 into D1 into 0.87 Fy plus Vu into SV divided by 2.5 into D1 into 0.87 Fy. So this equation is given for the transverse reinforcement in IS 456-2000. So in this equation we have to substitute all the values and we can get the SV. SV here is nothing but the spacing required. So you already know the value of TU. What is TU? TU is 50 kilonewton meter. And SV is what we have to find out. And B1 and D1 are the unknowns what we have to find out. Fy is the grade of steel which is 415 Newton per mm square. And Vu is the factored shear force which is given as 100 kilonewtons. And SV is what again we have to find out here. And D1 is an unknown, we have to calculate now. And Fy is the grade of steel which is 415. And ASV is already we have calculated which is 157.07 mm square. So first what are the unknowns here? SV is the unknown what we have to know and B1 and D1 are the unknowns here. So first let us calculate the B1 and D1 values. So now what we have to calculate the B1 and D1 values. So what is B1? B1 is nothing but the center to center distance between the corner bars in the direction of breadth. So what? So if you consider this particular rectangular beam section, what we have designed till now. So what we have designed that a two-legged stirrup of dia is how much? The diameter being 10 mm is provided. So let us draw that first here. So here I am going to provide a two-legged stirrup. So this is my two-legged stirrup I have provided, and the dia of this is 10 mm dia. The dia is 10 mm. So now let us calculate the B1. So what is B1? It is nothing but the center to center distance of the corner bars in the direction of the breadth. So if you take this particular figure, okay, so B1 is nothing but the center to center distance of the corner bars. Here these are the corner bars, okay, in the direction of the breadth. So what is the direction of the breadth? This is the direction of the breadth. So this is the direction of the breadth. So these are the corner bars. So the center to center distance is nothing but B1. So first let us calculate the B1. So what B1 will be? B1 will be equal to the total width or the total breadth of the beam, which is 300 minus, you need this distance, minus this is called as the, it is called as what? It is called as the clear cover. So this is going to be your clear cover. So this side you have one clear cover and this side also you have other clear cover, minus the clear cover minus clear cover, because you have to remove it from both the sides, minus what? It is the center, that is the center of this particular reinforcement, minus the diameter of bar by 2, because it is at the center. And in the similar way, this side also, minus diameter of bar by 2 will give you a D1. So the total width minus the clear cover this side and the clear cover this side minus the dia of the bar by 2 and the dia of the bar by 2 will give you a B1. So here I am assuming let the clear cover be 20 mm, because what? Previously we have already effective cover as 30 mm. Here I am assuming the clear cover to be 20 mm. That is, the clear cover is, we are not including the diameter of the bar here. So B1 will be equal to 300 minus clear cover is 20 minus 20 minus what is the diameter of the bar? It is 12 by 2 minus 12 by 2. So if you solve this, you will get a value of P1 as 248 mm. So the value of P1 is how much? It is 248 mm. So now in the similar way, let us calculate the D1 value. Now let us calculate the D1 value. So what what is D1? D1 is nothing but the center to center distance of the corner bars in the direction of depth. Here what? It is the direction of the depth. Here B1 is in the direction of breadth and D1 is in the direction of the depth. That is, in this direction we have to calculate the D1. So in the similar way, what D1 will be? D1 is equal to the depth of the section. So what is the depth of the section? It is 600 minus the clear cover on both the sides. So the clear cover is 20 minus 20 minus the dia of the bar. So here the dia of the bar is 20 mm and here it is 12 mm. So we have to consider both. So one will be 20 by 2 minus the top side reinforcement. It is 12 by 2. So from this you can calculate the value of D1. So if you do this, you will get a value of D1 as 544 mm. So what? Now we have got the values of B1 and D1. So D1 being 544 mm and B1 is 248 mm. Now substitute these values in the equation, that is the transverse reinforcement equation, which is ASV is equal to TU into SV divided by B1 into D1 into 0.87 Fy plus BU into SV divided by 2.5 into D1 into 0.87 Fy. So in this equation substitute all the values. We already calculated the value of ASV, which is what? 157.07 mm square is equal to. So TU you have already known, which is 50 kilonewton meter into SV divided by B1 we have calculated now, which is 248 into D1 we have calculated, it is 544 into 0.87 and the grade of steel is 415. So for the stirrups, the maximum grade of steel what you have to provide is 415. Either you can provide 250 or you can provide 415. So here I have provided 415 grade of steel plus VU. VU is how much? VU is 100 kilonewton. So 100 into 10 cube into SV divided by 2.5 into D1. How much is D1? D1 is 544 into 0.87 into 415. So if you solve this, you will get a value of SV. That is the vertical spacing required. So if we will solve this, we will get a value of SV as SV is equal to 127.67. So this is the spacing which is required, which is 127.67 mm. Now what? We have to check for the minimum spacing. Now we have got the spacing as 127.67 mm. So how the transverse reinforcement is provided? The transverse reinforcement is provided in the form of vertical stirrups. The spacing of the transverse reinforcement should not, that is the spacing which you are providing here should not be greater than x1 plus y1 by 4 and 300 mm, whichever is this. So out of these three conditions, that is x1 plus y1 by 4 and 300 mm, you have to take the lesser value, and the spacing what you have what you are providing here should not exceed this value. Okay, that is the least value in this. What you are taking, that particular value. Okay, it should be less than the SV. That is, you have to find out all these and you have to consider the least value in this, and this particular SV should not be more than these values. So now we will calculate x1 plus y1 by 4. What is meant by x1 and y1. So for that, what I am going to do is, I am going to redraw this figure here, showing the two-legged stirrup. Showing the two-legged stirrup. So this is the top reinforcement what we have provided. This is the side face reinforcement. This is the bottom reinforcement. So this is the stirrup. This is the stirrup of two-legged stirrup of 10 mm diameter. So what is x1 and what is y1? x1 is nothing but the center to center distance of the stirrup. Okay. So your beam will be like this. This is our beam. Okay. This is our stirrup. This is our beam and this is a reinforcement. So the center to center distance of the stirrup, that is the short distance, is taken as x1, and the longer distance of the stirrup center to center is considered as y1. So what will be your y1? This is going to be your y1. So x1 is the center to center distance of the stirrup which is short, and y1 is the center to center distance of the stirrup which is long. So now let us calculate the x1 and y1 values. So x1 will be what? So x1 will be the total breadth minus the clear cover 20 minus 20 minus the dia of the stirrup divided by 2 on this side as well as this side. So what is the dia of the stirrup? It is 10. 10 by 2 minus 10 by 2. So if you solve this, you will get a value of 250. Now let us calculate y1. So y1 is equal to the depth, which is 600 mm minus the clear cover 20 minus the clear cover 20 minus the dia of the stirrup by 2 minus the dia of the stirrup by 2, which will give you a value of 450 mm. So what is the condition? So we should take the least value of x1, which is 250 mm, and x1 plus y1 by 4. So x1 is how much? It is 250 plus 450 divided by 4, which will give you 175 mm. So this is going to be your one value, and the other one value is, this is 1, this is 2, and the third one is 300 mm. So out of all these three, what you have to consider the least value. So out of all these three, what is the least value? 175 mm is the least value. Now what? The spacing SV should not be greater than the least of all these three. So what is the least value? It is 175 mm. And the spacing what we got here is 127.67 mm. So this is not greater than 175 mm, hence it is okay. So what we have to provide? we have to consider this spacing. Okay, so what I am doing here, I am considering a spacing of 120 mm. The vertical spacing I am considering as 120 mm, and the dia of the stirrup I am providing it as 10 mm two-legged stirrup. So provide two-legged stirrup 10 mm diameter, spacing, this I am considering 120 mm center to center. So that center to center distance of each stirrup of dia 10 mm is 120 mm is 120 mm. Now what? I have to check for the minimum spacing. Okay, that is, I have to check for the transverse reinforcement. That is, the ASP should always be, that is the ASP what I have provided, that is the area of the vertical stirrups what I have provided, it should be always greater than what I have calculated now. So now let us calculate the ASP, and the ASP provided, it should be always greater than the ASP what we are going to calculate. Now the total transverse reinforcement what we have provided should not be less than tau PE minus tau C into B into SV divided by 0.87 Fl. So the total transverse reinforcement what they have provided should be always greater than or equal to, okay, to this value. Okay, it should not be less than what we have calculated from this one. So substitute all the values here. So we already know the value of tau E. It is 2.14. And tau C is, it is nothing but the shear strength of concrete. So it depends upon what? It depends upon the percentage area of the steel. So let us calculate the percentage area of steel. How we will calculate? It is AST by BD into 100. So AST previously we have calculated how much we got? It is 1570 into 100 divided by B. B is how much? It is 300 and D is 570 mm. So from this you will get the percentage area of steel as 0.918. So what have you calculated tau C from table 19 corresponding to this 0.918, you have to take the tau C value. So by interpolation if you do, you will get the value of tau C as 0.59 Newton per mm square. So this tau C value is for what? This is for the area of steel what we have provided. So now substitute all the values here. So tau B. So tau B is what? Tau E is 2.14 minus tau C. Tau C is 0.59 into B. How much is B? It is 300 into SV. So how much is the spacing I have provided? The spacing I have provided, it is 120 mm divided by 0.87 into 415. So if you calculate this, you will get a value of 153.6 mm square. So what we have provided ASV? The ASV we have provided is 157.07 mm square. So it is greater than this value. So the total transverse reinforcement what we have provided is more, hence the design is okay. So what we have designed the reinforcement, the longitudinal reinforcement, which is here we have the bottom reinforcement as 5 bars 20 mm dia, side reinforcement as 2 12 mm dia bars, the top reinforcement as 2 12 mm diameter bars, and we have provided the two-legged stirrup, and the dia of the stirrup is 10 mm. So in this way we have to design the reinforcement when a torsional moment is considered or when the torsional moment is given. Thank you.